All right, today we're diving into a material that is, and I mean this literally, foundational to our planet. But it could also be the foundation for our entire future. It's a substance with a deceptively simple recipe, but one that holds just an incredible amount of power. So let me just ask you something. What if I told you there's a single class of material that makes up the vast majority of our planet's mass and also holds the key to next-gen solar panels, mind-blowing data storage, and even revolutionary medical tech? Sounds a little like science fiction, right? Well, the material we're talking about is called perovskite, and it's estimated to make up a staggering 50% of the Earth's total mass. Yeah, half the planet. Most of it is deep, deep beneath our feet, the dominant material in the planet's mantle, all formed under just immense heat and pressure. So in this explainer, we're going to go on a bit of a journey. We're going to start in the deep earth where this stuff was born and travel all the way to the high-tech labs where its incredible potential is being unlocked right now. Now, perovskite isn't exactly new. It was actually first discovered way back in 1839 over in Russia's Ural Mountains. But for most of its history, it was just a geological curiosity. It really wasn't until the 2000s that scientists truly started to figure out what makes it so special. And that led to an absolute explosion of research that's unlocking its secrets as we speak. So, what is the secret? What makes this stuff so special? It all comes down to its incredibly simple, yet unbelievably flexible chemical recipe. The best way to think about it is like an atomic Lego set. The entire blueprint is just ABX3. That's it. It's made of just 3 building blocks: a large, positively charged atom, which we call the A cation, a smaller positive one, the B cation, and a negative one, the X anion, which is usually oxygen. And this is where the magic really happens. You see, those A and B slots aren't fixed. They're just placeholders. Scientists can plug in a huge number of different elements right from the periodic table, mixing and matching them to design a nearly infinite library of new materials, each one with its own completely unique properties. Okay, so we've got our atomic building blocks, but how do these simple ingredients, our A, B, and X, actually stack together to build the final crystal? Well, it starts with the most efficient way nature knows how to pack spheres, something called close packing. Just picture arranging a layer of marbles on a table so they take up the least amount of space possible. That's pretty much the first step, creating these dense 2D layers of atoms. Then, you just stack them up. The next layer of atoms settles right into the gaps of the one below it. And by stacking them in this specific offset pattern, we call it an ABC sequence, you start to build up a stable 3-dimensional crystal lattice. But this stacking isn't perfectly solid. It creates these tiny, predictable, empty spaces between the atoms. And these spaces, or voids, are absolutely crucial. They become, basically, the designated parking spots for the other atoms in a recipe. So when we put it all together, the crystal just kind of builds itself. The large A atom slots right into that big empty space in the very center. The smaller B atoms take their positions at each corner of the cube, and then the X atoms lock into place on the center of each face. It's really elegant. And this is the beautiful result. It forms this stable, repeating framework of 8-sided shapes called octahedra, all connected right at their corners. That elegant and strong atomic architecture, that's the secret sauce behind perovskite's incredible properties. But okay, here's the twist. That perfect, ideal structure we just built, it's actually pretty rare. The real magic of perovskites, the thing that makes them so special, comes from their imperfections, these tiny distortions that actually unlock their superpowers. You see, that perfect cubic structure only forms when the atoms are exactly at the right size to fit. But what happens if an atom is a little too big or a little too small for its parking spot? Well, the whole crystal has to bend and twist and tilt to make room for it, kind of like adjusting a bookshelf for a book that doesn't quite fit. And those little adjustments, that's where things get really, really interesting. Let's take a concrete example, okay? In one of these distorted structures, the positive and negative charges are already a little bit off balance. Now, if you apply physical pressure, you literally squeeze the crystal, the atoms shift even more. This separates the positive and negative charges, and poof, you've created an electric voltage. That amazing property is called piezoelectricity, and it's used in countless sensors and actuators already. And that's the crucial point here. This ability to distort, to be flexible at the atomic level, is exactly what makes perovskites a true wonder material. It's the key that unlocks an almost unbelievable range of applications. And, this quote from the source material just sums it up perfectly. It's the flexibility of the structure that is directly responsible for the variety of its properties. Change the atoms and you get a different distortion, which in turn gives you a completely different physical behavior. It's that simple. And the variety is just stunning. By tweaking that recipe, scientists are creating everything from ultra-efficient solar cells that could revolutionize our energy grid, to new forms of data storage, even superconductors that transmit electricity with zero resistance. We're also seeing them in lasers, sensors, industrial catalysts, and even for targeted drug delivery in medicine. The list of possibilities just keeps on growing. And get this, the innovation isn't slowing down, not at all. Scientists are now creating what they call hybrid perovskites, where they swap one of the atoms for a much larger, more complex organic molecule. This adds a whole new set of dials to turn, giving them even finer control and opening up pathways to properties we probably can't even predict yet. And that brings us right back to the key takeaway. It all comes back to that simple ABX3 recipe. A simple starting point that, through atomic substitution and this amazing structural flexibility, gives rise to a nearly infinite library of materials, each one fine-tuned for a specific purpose. Which, of course, leaves us with one final, fascinating question. We have a material that makes up half our world, and a recipe book that's nearly endless, so the only real limit, when you think about it, is our imagination. So what monumental problem do you think perovskites will solve next?